Hello, my name is Garegin Grigoryan, and I am a PhD candidate at Rochester Institute of Technology. Today, I'm going to present my paper, Boosting FIB Caching Performance with Aggregation. This paper is co-authored with my advisor, Professor Minseok Kwon and Dr. Yaoqing from Fairleigh Dickinson University. Networking is growing today. The number of users is increasing with the spectrum of services provided online. High-performance distributed computing is one of them. Obviously, it highly depends on fast packet forwarding. Today, I will talk about one of the main contributors to packet delay, route lookup. Let's have a look at a simplified illustration of route lookup. ISP routers contain large BGP tables with destination prefixes and next hops. These tables are also called forwarding information bases. When a packet arrives at a router, its destination IP address is matched against the prefixes in the routing table. The longest match is selected to obtain the next hop. The matching is performed in TCAM memory at the line speed. In this example, the IP address matched two prefixes, and the longer match with 90 bits length is selected. The packet is then sent to the next hop D. BGP tables stored in routers continue to grow. In the IPv6 future, they will be even bigger due to the large IPv6 address space. This results in the routing table overflow problem. Since TCAM memory is constrained and energy hungry, operational expenses for TCAM upgrades are very high. The price of a Cisco router with TCAM can reach tens if not hundreds of thousands of dollars. Moreover, larger TCAM consumes even more energy, and on this slide I'm talking about this example in Japan where the total router energy consumption today is comparable to the total energy produced in the country in 2005. How to deal with TCAM overflow problem? Well, we can filter some addresses, decrease allocated space for IPv6 prefixes, or use cheaper memory. All of this approach will affect network reachability or degrade packet forwarding performance. For example, a prefix lookup on DRAM is 7 times slower than a prefix lookup on TCAM memory. Finally, there are two approaches thoroughly studied by academia. First, FIB aggregation, merging adjacent prefixes with the same next hop, and then FIB caching, offloading FIB from unpopular routes. In this work, we merged these two well-known approaches. Our research had been motivated by two factors. First, we verified multiple observations that most of the prefixes in the routing table carry a tiny portion of the total traffic. Second, after building our own FIB caching architecture, we identified that in its prototype, its caches are compressible by 15%. However, for building such an architecture, we face a critical challenge. The optimal FIB aggregation algorithm creates overlapping routes, which will trigger a well-known problem called cache hiding, when the longer prefixes hide in the secondary memory, and so the longest prefix match in the cache is actually not the longest one, and so is incorrect. So let me summarize the design goals we set before we started working on this project. On top of the existing FIB caching architecture, PFCA, we wanted to design a FIB aggregation and incremental BGP update handling algorithms. Both algorithms needed to avoid generating overlapping routes and hence prevent cache hiding. The key insight into our solution is that in the control plane we use the binary prefix trees for aggregation, and only one prefix per branch of that tree can be installed into the FIB. For the data plane, we continue to build our solution on top of the programmable switch architecture. In the rest of this presentation, I'll give you more details on some of the components of our new solution, and I will present evaluation results. Let me begin with a short background on programmable and portable P4 switch architecture we leverage in this work. Unlike standard routers and switches, programmable switches have several properties essential for building our solution. First, they allow register encounters for storing inside the data plane. This is helpful for conducting cache monitoring, specifically identifying potential cache entries and cache victims. Second, with P4 we can program the ingress pipeline of the switch through different tables, in our case 2 levels of cache and a slow FIB. On this slide we can see the entire architecture of CFCA, combined FIB caching and aggregation. Like any router, CFCA's router has a separate control and data plane. The control plane is responsible for the management of forwarding tables. First, it needs to extend initial prefixes to avoid overlapping routes. Second, it needs to perform the recursive FIB aggregation. Finally, it needs to handle BGP updates correctly while keeping the FIB in the compressed state. Let's have a look at CFCA's FIB processing. Initially, CFCA builds the binary prefix tree from the prefixes received by BGP. On this graph, the solid nodes are the nodes derived from the original routing table. The dashed nodes are the fake nodes. They are auxiliary nodes in this binary prefix tree. The gray nodes are the nodes that are considered to be in the routing table. Obviously, at the very beginning, the gray nodes are also the solid nodes because they are derived from the original routing table. Each node contains a label, a name. Also, it contains an original next hop and the next hop obtained after the aggregation process. After the initial binary prefix tree is built, CFCA performs leaf pushing, after which the leaf nodes represent the set of non-overlapping prefixes. The routing table will still have the same identical forwarding behavior as the original routing table. Note that the new dashed leaf nodes appeared at the binary tree. Now CFCA performs the initial FIB aggregation. The siblings with the same next hop recursively merge into their parents. If siblings have different next hops, they become so-called points of aggregation. Their ancestors will not be placed into the forwarding information base. As you can note, only one prefix per branch is installed into the FIB. Those are the gray nodes. Now let's look into a BGP update handling example. Suppose 2 BGP updates were received by the control plane. Prefix corresponding to the node C was updated with the next hop 2, and the prefix corresponding to the fake node H was announced. So the node converts to the real type. So the H node now will become a solid node. After the nodes updated themselves, as you can see, C and H just changed their original next hops. CFCA needs to update the aggregated parent node of C and the derived node for H. Now F and C have different next hops, and they must be disaggregated and converted into the points of aggregation. On the contrary, I and D merge into H since they have the same selected next hop. To give you the general idea, the process of BGP update handling is similar to the initial aggregation process in CFCA. The main difference is that it begins at the updated node and the traversal stops at the first node that has not been affected by the update. To get more details on BGP update handling algorithm of CFCA, please look into the paper. Let's move on to the forwarding or data plane of CFCA. First of all, it is responsible for forwarding packets. CFCA has three types of tables: level 1 cache on the fastest memory, level 2 cache, and a popular prefix table on DRAM memory. On L1 hit, the packet is forwarded through the light traffic headers filter for identifying potential cache victims at the line rate. We will talk about that filter a little bit later. On L1 miss, the packet is forwarded to the L2 cache and the slow FIB in parallel. L2 hit is treated similarly to L1 hit. Otherwise, the packet's destination IP address will or will not find its match in the slow FIB table. The table entries in the data plane are attached with counters. On reaching a predefined threshold, an entry is considered as popular and is moved to the faster memory. If the faster memory is full, a victim cache entry is evicted and replaced with the new cache entry. One of the challenges for FIB caching is how to identify potential victim cache entries in a large routing table at the line rate. Let's look at this example. Obviously, sorting or algorithms like LRU cannot be implemented on the data plane. And in any case, those algorithms will not be able to keep up with the traffic rate. One of the possible ways to solve this is to use hash tables and compare counters of the collided prefixes upon each prefix match. So let's look into such an example. Here the prefix 1011 with 2 hits was a recent match, and we compare it with another prefix in a hash table. So the prefix 1011 collides with another prefix 0011, and that another prefix has 4 hits. Since 1011 is less popular, it replaces 0011 from the list of potential victim cache entries. The problem of this approach is that two popular prefixes may collide in the same row, and one of them will always stay in the table. In CFCA, we use distributed hash tables with different hash keys to avoid such a situation. Light traffic headers filter was inspired from a SOSR paper in 2017. We used it in our earlier work dedicated to a pure FIB caching architecture, PFCA. The filter is located inside the data plane, and its goal is to collect the least popular entries. Initially, the tables are empty. On each match, the matched prefix and its counter are pipelined through the filter. Here, the first prefix arrives, and its hash value in for the stage 1 table is 2, and so the prefix and its counter are placed into the first table, the second slot. If there are other matches with the same prefix, its counter is updated too. As you can see, if you look at the second slot of the stage 1 table, the counter goes up. Other prefixes also populate the filter. Upon collision, the prefix counters are compared, and the more popular prefix is pushed into the next table in the pipeline. Here you can see the prefix 10101 with the counter value 1 is compared against the prefix 10110 with the counter value 3, and that entry is at the second slot of the first table. Because that entry is more popular, it is pushed into the second stage table. In the second table, the hash function is different, so it's very possible that there will be a different slot for the prefix compared to the table stage 1. Eventually, all tables are full and the more popular prefixes are driven out from the filter by less popular prefixes. In this example, the newly matched prefix pushes the other prefix 1001 from the table of the first stage. So the hash value of the prefix 11101 is 1. It collides with the first entry in the stage 1 table, and because that entry is more popular, it is pushed out to the stage 2 table. The prefix 10001 in its turn pushes out the prefix 10011 from the stage 2 table because there is a collision, and because the prefix 10001 is less popular. Finally, the prefix 10011 collides with the first entry of the stage 3 table because its hash function for 10011 at the stage 3 table is 1, so the collision happens with the prefix 11011, and that prefix is less popular, so it stays in the table of the first stage. So the prefix 10011 with 6 hits is removed from the filter. Now we will move to the evaluation of CFCA. For this experiment, we built a simulation-driven prototype. We used 2 different traces, one with 3.5 billion of packets from Qaeda and up to 46,000 of BGP updates from route views. We also used a heavier trace with 7.7 billion of packets and more than 1 million of BGP updates, also from Qaeda and route views. We set our caches to only 2.5% of the full FIB for L1 cache and 3.3% of the full FIB for L2 cache. We compared cache miss ratios between CFCA and a pure FIB caching solution, PFCA, stability of L1 and L2 caches, and the BGP update churn. We wanted to evaluate BGP update churn as it might have been affected by the aggregation layer added in CFCA. In addition, we compared how fast the control plane of CFCA can handle BGP updates compared to the optimal and suboptimal FIB aggregation algorithms and a FIB caching solution. On this slide, we can see that the average cache miss ratio for CFCA is much smaller than for PFCA, a pure FIB caching solution. We attribute these results to aggregation that frees significant space in L1 and L2 caches. The L1 and L2 caches in CFCA are much more stable. The churn in L1 cache is minimized by 46%. This is essential for TCAM memory as insertion and deletion operations on TCAM are expensive. BGP churn naturally increases after FIB compression. Indeed, CFCA's BGP churn is slightly higher than PFCA's. However, it remains extremely small. Most of BGP updates do not affect popular routes. In our case, less than 1% of the total number of BGP updates affected L1 cache. A heavier 1-hour trace with 7.7 billions of packets and a larger BGP update trace resulted into an increase of cache misses. This is natural since the frequency of packets is significantly higher. However, the number of misses is still very low. Moreover, with this trace we were able to evaluate how fast CFCA handles BGP updates. In comparison to the optimal FIB aggregation algorithm ORTC, CFCA is faster by 77%, and it is still faster than a suboptimal FIB aggregation algorithm FAX. To summarize, CFCA presents two levels of cache on TCAM and SRAM memory. While cache misses are entirely managed in the data plane without redirection to the slower control plane, their number is significantly lower than in a pure FIB caching architecture. CFCA shows lower cache churn and efficient BGP handling. The key takeaways from this talk is that FIB aggregation and caching are beneficial for fast packet forwarding via TCAM. Aggregation and caching can work together with CFCA's control plane, increasing cache hits compared to pure FIB caching, and reducing cache churn and time costs compared to pure FIB aggregation. In our future work, we plan to implement CFCA's full prototype with P4 language based on portable switch architecture. Thank you, and I will be glad to answer your questions.